Yeah, I want to thank the organizers for giving me the opportunity to speak here. So this talk is a continuation of David's talk, and I say something about how to lift these non-geometric fluxes to a double field theory setting, because this sheds some light on how they can be interpreted geometric. So I want to rewrite a very particular double field theory action, which is particularly convenient for our purposes. And I want to show how this can be reformulated in a way that we have a kind of geometric interpretation of these non-geometric fluxes, at least in the double field theory setup. And then I show how that can be connected to the 10-dimensional supergravity setup we have seen in this last talk. So the strategy is the following. First of all, we want to perform the same field redefinition in the renewed language of double field theory, and that we do in this formulation where you have a quantity E tilde, which is basically the sum of G and B, which has the advantage that each term in this action is T-duality invariant separately, what we're going to use later on. And secondly, we try to covariantize the result of this field redefinition with respect to half of the double field theory gauge transformations. And that in particular means that we introduce a covariant winding derivative, this object here, and a new winding Riemann tensor, this object here, R check. So let me start with the field redefinition. I'm doing that in 3 steps, where first of all we realize that this equation in red is exactly the equation David showed us just a second ago. And this thing on the right-hand side is unfortunately the inverse of the curly E, which appears in the double field theory action. So we have the problem that there appears an inverse in the field redefinition. But step 2 now says that if you look at T-duality in general in double field theory, you find this transformation rule here given by some ODD matrix H, A, B, C, D. And in particular, you can note if you set B and C to 1 and A and D to 0, you exactly get the inverse. So somehow it seems that T-duality might help to formulate this field redefinition. But you note also that the coordinates transform accordingly. So in the special case I just mentioned, you find exactly what you need. And step 3 then is that we compare the quantities we want to equalize. This G tilde, the new metric, and beta. And on the right-hand side, you find the transformed quantities after T-duality, G prime, B prime. And you read off some rules for the field redefinition, which include that you replace the metric by this tilde metric and B field by the beta. And additionally, you interchange the derivatives because the coordinate dependence changes. Yeah, I mentioned already that you can do this term by term, so it's especially easy. And the dilaton density, just as a side remark, is something that remains unchanged. So effectively, the field redefinition is simply inverting all indices. So we take the double field theory action in this particular formulation, and we just replace everything with index down by something with index up, and vice versa. So so far we haven't employed any computation on this. That was quite easy. The next thing is that we want to read off where the non-geometric fluxes appear in this formulation. And therefore we look at the gauge symmetries of double field theory. They are parametrized by this SODD vector. And if you now find some covariant objects with respect to the psi gauge transformations, so the vector part, you can formulate some geometric origin of the non-geometric fluxes. So covariant for us means that objects transform like tensors. We start with scalars and find that the tilde derivative, so the winding derivative of a scalar, is not a vector, but we can introduce a new derivative, d tilde, which involves an ordinary derivative contracted with a beta to give something covariant. And curiously, it already appears that non-geometric fluxes are given by a commutator of these 2 derivatives, where R flux is just derivative on beta. Next step is that we broaden that to tensors. So we define a covariant derivative for vectors using a new connection symbol gamma check, And we constrain it by these two equations, where we first claim some kind of metricity condition, and secondly, we want that the commutator of two derivatives acting on a scalar is simply given by a covariant object, which is the R flux. If we do so, we find that this new connection symbol is simply a connection symbol, a Christoffel symbol, given by the new d tilde derivative plus some terms that involve q. So in a sense, the antisymmetric part of this connection, gamma check, is given by the q flux. So that's step one, to identify a geometric interpretation of these non-geometric fluxes. And finally, we can define a Riemann tensor in a more or less standard way, where we commute two derivatives acting on a vector, and we find that it is given by some expression that might look familiar, where we simply replaced all derivatives by this new d tilde derivative. But additionally, in the second line, we find that the non-geometric fluxes enter this Riemann tensor directly. Then we define a scalar curvature, like usual, with the contraction of the Riemann tensor, and eventually we can formulate the double field theory reaction we have just obtained after the field redefinition, given by these five quantities, where we have a scalar curvature based on the ordinary derivative, and another scalar curvature that is based on this new derivative d tilde. Those appear here. It's just the sum. Then we have the R flux, which is entering as a tensor contribution exactly in the same way as the H flux enters. And then we have two dilaton terms, both of them, one of them with the ordinary derivative, and the other one as well with the d tilde derivative, the new thing. And then additionally, we have to add a tensor tau I, which is needed to match, and is given by the trace of the gamma check connection symbol. So let me note once more that each term of this new action is now covariant under Xi gauge transformation. So again, that is half of the double field theory gauge transformations, and these are made manifest by this approach. Of course, the action is still invariant under the other half of the gauge transformations, but that is in a non-trivial matter, so we have to combine different terms. And more importantly, we have found now that the q flux just enters as a part of the connection, and that is very similar to how the geometric flux f enters the other scalar curvature. And the R flux simply appears as a tensor, like the H flux did before. So in a double field theory setup, we have kind of a geometric origin for these fluxes. And to make contact to the 10D supergravity formulation of all that, we first note that you can, of course, reduce double field theory in this curly E formulation by simply setting the d tilde derivatives to 0, which is the solution to the strong constraint. And you then find the ordinary supergravity and SNS sector given by phi, g, and b. And we have seen that performing a field redefinition there brings you to a supergravity formulation in terms of phi tilde, g tilde, beta. And the same thing we get if we take the double field theory action I just presented and do the same thing. We're setting all the d tilde derivatives to 0. So in a sense, we have obtained the same result in 10 dimensions, but going this detour over double field theory, having an easier computation and additionally some kind of geometric interpretation. And finally, I want to mention that some recent results in this topic match nicely to what we find. For example, there are some expressions for the R flux around when people did Shirk-Schwarz reductions of double field theory, for example, Aldazabal or Geisbühler. And this expression is exactly the expression we have, which was the d tilde derivative on beta. And also some of the Di Bianchi identities Ralph mentioned yesterday, you can reproduce, for example, by just taking the covariant derivative of the R flux. So to sum up, I want to emphasize that double field theory in some sense allows for a geometric interpretation of non-geometric fluxes.
Questions? In David's talk, he threw away a total derivative and going through the field redefinition in his action. How is that looking like in the double field theory language? Do you do the same, or is it clear?
Yeah, I mean, all the connections I drew are up to total derivatives in many places, but finally, at least, you have it when you do this step. So, for example, it's well known if you go from here to here, this is not matching exactly, but matching up to a total derivative. And the same occurs on the other side. So, yeah, you have total derivatives as well. And they are basically the same, yeah? So there's nothing unique.
Make a comment on that. Yeah, if you combine those total derivatives with the Gibbons-Hawking term, which is a total derivative in gravity, then that itself becomes a boundary term in the double field. But you need to combine those two things together.
I don't see any more questions, so we thank Peter again.